Alrighty, geometry friends, welcome to chapter 2. You made it through chapter 1, and so well done. And if you had a rough start in chapter 1, chapter 2 is kind of a fresh start because what you're going to see is it's on reasoning and logic, and so you're not going to have a lot of arithmetic or algebra in this chapter, but it's going to be a little bit of writing and sentence and statement making in order to practice some reasoning skills. And we're going to learn a couple different types of reasoning and how to form logical arguments. So 2.1 is on inductive reasoning. So we got the definitions and questions for 2.1. And so the first type of reasoning that 2.1 covers is inductive reasoning, which basically means that you're going to draw a conclusion based on patterns. So it's the ability to kind of say, okay, this is true, or this is what comes next because of a perceived pattern. So if somebody were to say, okay, 2, 4, 6, 8, kind of the idea of, okay, so what would come next? You could perceive, okay, 10, because I can use my inductive reasoning to see that you're counting by even numbers. And so the next thing that comes would be 10. Another example might be something like somebody says Monday, Wednesday, Friday, ... It would be inductive reasoning. You try to draw a conclusion based on that pattern that, okay, they're counting every other day of the week. So after Friday, skip Saturday, it would be Sunday. And so there, you're perceiving a pattern and drawing a conclusion. That is inductive reasoning. So secondly, there's these things called a conjecture. What is a conjecture? That is a statement based on inductive reasoning. Another word that I might write up there is a conclusion. So when you look at a certain pattern, can you draw a conclusion? Or maybe another thing you could say is it's like a rule that you can make using inductive reasoning. For example, if I were to have a pattern that looks something like this: 3 plus 5 equals 8, 2 plus 4 equals 6. And what I'm doing is I'm adding even and odd numbers. 1 plus 7 equals 8. And what I'm finding is that whenever I add 2 even numbers or 2 odd numbers, so here's 2 more even numbers, 4 plus 10 equals 14, I can make a conjecture that the sum is always even. This is just one example. So I can see based on that pattern, anytime I add 2 odd numbers or 2 even numbers, then they must equal an even number. And so my conjecture would be that adding 2 even or odd numbers equals an even number. And now I make that conjecture and I based it on some evidence. I did a couple examples, but whether or not that's true could still be decided. You don't know if a conjecture might either be true or false. You have to decide if you can prove it or not, or disprove it. But just making the statement based on inductive reasoning is a conjecture. So there's my conjecture. I believe it to be true, but you can evaluate it if you want. See if you can find a counterexample to prove my conjecture wrong, but it still is a statement based on inductive reasoning. And that takes us to our third vocab, which is counterexample. And that is how you prove a conjecture false. If someone makes a statement like the one I made above, and you can find an example that proves it false, that's a counterexample, and therefore the statement is untrue. One counterexample proves a conjecture false. That might be something we add here. Is it only takes one. Whereas you can sit there and give countless examples of it being true, and you can do it again and again and again, and it's not necessarily proven true yet, but you just need one counterexample to prove that it's not true. Here's an example. Like someone might make a conjecture saying any 3 points form a plane. Any 3 points form a plane. I think this one actually got some of you on the last test. Okay, that's a conjecture. And so I could do a series of patterns and be like, okay, here's 3 points. I formed a plane. Here's 3 points. That forms a plane. Here's 3 points. That forms a plane. And so based on that pattern, that conjecture looks pretty good. But there is a counterexample, or a lot of times an exception to what seems to be a rule, and that is, what if I do this? and I put 3 points in a perfect line. Or in other words, if I have 3 collinear points, that is not a plane, that is a line. And so that would be a counterexample to this conjecture here, proving it false by giving an example of 3 points. I could write it out. 3 points could be collinear. Okay, and so a counterexample could be a drawing, it could be a statement, it could be, let's see what it says here, 3 things. It could be a drawing, a statement, or even a number. So even there, I could use my drawing there, and then here's my statement. So that would prove this counterexample of any 3 points forming a plane to be false. And what you're going to find out is this actually helps us to write good definitions, because the definition of a plane is any 3 non-collinear points form a plane. Okay, so that takes us to some of the questions then from 2.1. The first one is, how do you prove a conjecture false? Well, you're welcome for making these so easy. We just talked about it. You have to use a counter example. For example, say somebody, we'll just do one other example. Say somebody makes the conjecture and they say the sum, which means to add them together, of any 2 numbers is positive. Okay, so if you add up any 2 numbers, you're going to get a positive number. 1 plus 3, 1,000,000 plus 5, 50 plus 60. Those are all positive. However, here's a counterexample to that. The sum of any 2 numbers is positive. Well, what about -5 plus 2? That's a sum. That's using addition. But you can see the answer to that would be -3. And so that is a counterexample, and that is how you prove a conjecture false. And it only requires 1. Okay, question number 2 says, how do you prove a conjecture true? The answer to this is, I'm going to say, in a way, you almost can't. It's from a lack of counter examples. In logic and reasoning, now it's not entirely true, because we can prove things that we can be certified to be true. There are things called proofs. But in general, what I want you to take from this is that the conjecture is true until you find the counterexample. I should say counterexamples. You only need 1. So lack of counterexample. So if something is true, but it's only true until you find that 1 counterexample. And that's the truth of even in science, is we have many statements and theories and laws, and we're pretty sure they're true, but it's only true until someone finds that one rule, that one exception that breaks the rule. And then that causes us to have to go back and refine our counterexample. Like, for example, if I went back to number 1, because I found that counterexample, I could rewrite the idea of the sum of any 2 numbers is positive. And I could say, well, maybe the sum of any 2 positive numbers is positive. And if I modify it, then I can get closer to having what hopefully is a true statement, unless somebody can find another counterexample. Number 3 is just a little bit of practice. Simple stuff. Identify the next 2 terms. So some of the problems today, you'll be trying to identify patterns. You can see here, we can see the difference between each number is 3. So it looks like this is a simple one, just to get you to, we're just counting by 3. So that would make our next number 18, and then our next number 21, 19, 20, 21. So that's a really basic one. Some of them will be maybe a little more tricky, but that is using our inductive reasoning to make a statement. And finally, 4th problem, just for the notes section of 2.1, we have make a conjecture about the product of 2 odd numbers. Okay, so the product means to multiply. So it's saying what happens when you multiply 2 odd numbers? I have no idea. Let's find out. Let's just kind of start to establish a pattern. So 3 times 5, well, that's 15. 1 times 7, that's 7. 7 times 5, oops, didn't work. 7 times 5, 35. 5 times 9, 45. Well, the only thing I can see emerging is, notice all of my products are odd. So I'm wondering if the product of all odd numbers of two odd numbers must always be odd. I wonder if you could think of, is there any two odd numbers when you multiplied them, you actually got an even number? My guess is it's going to be no. And so that's going to be my conjecture. The product of two odd numbers is it, let's see, no, numbers, yeah, numbers is odd. And that is true until someone can find a counterexample to disprove it. Alrighty, so kind of our introduction into reasoning. It's going to require us to be a little kind of slow and steady in our thought processes. It's going to be very precise in the language that you need to use as we move through these lessons. But 2.1 is again on patterns and the conjectures you can draw from them and the ability to prove those conjectures false using counterexamples. Alrighty, see you for the classwork for the exercises.